My my second talk. I'm going to talk about Legion Prof and the Fuzzer. So should I lower this because it feels like it's okay. Okay. So since last retreat, it feels like we almost have a completely new system. So I think it was literally in the last retreat that we were talking about the design for a scalable UI. And after that point, I went home for Christmas and wrote it over my break. So that was sort of fun. I came back and demoed it, and it completely blew the old system out of the water. So unfortunately, I don't think I have that demo ready to go here. But in the previous time when I demoed it, I started the old UI, and I let it sit there. And I popped up the new UI, and I talked through all the features. And by the time I was done talking through all the features, the old UI was still loading. So it feels like a completely different world in terms of how usable and responsive the system is. But we have also just like a boatload of new features. We have Mike put in critical paths, so you can determine, what was the thing blocking your task execution. We have backtraces on all your wait points, so when you're blocking on something, you can figure out what's causing it to block. We have provenance. There's some skew detection in the code now when your clocks are not aligned. We have Mike put in a whole bunch of effort to figure out exactly what when you're calling into some sort of a runtime call, correctly identifying which task that's associated with. And some user-provided profiling information, and actually reporting what the kernels are doing in your GPU as opposed to just the host code, and a whole bunch of fixes for other stuff. Yeah, so some of the things that we've been doing. So we start to report now, if you accidentally capture a profile in debug mode, it brings up a nice bright red warning at the very top of the profile that tells you that you're doing that. And I think that the next version of that we want to do is including the machine configuration. So if you have misconfigured your Slurm so it binds your process to one core, that would be bad. And so what we can do is we can capture that information in the profile itself. So ideally, it pops up that red warning. And then we can go and investigate, right? Because the way we typically use this is user has some sort of a problem. The very first thing we always ask for them for is show us a profile, right? So it would be really helpful if profiles capture all of the things that we need to debug that stuff. Beyond that, we've been thinking about some other ways to consume the data. So one of the things that's been requested a bunch that hopefully we'll get on is being able to dump an actual database, like a SQLite database, with the contents of the profile so that you can run arbitrary scripts on that. There are a couple of sort of UI improvements that I think we'll work on. And then some of these things, I won't go through the stuff that's a bit further out. Yeah, so I'm going to dig a bit more into some of the specific things that have changed. This is sort of the way that the architecture looks. So you have your application on the left-hand side. So you're running Legion. Legion is generating your profiles. So we dump some logs out to disk. And then this is an offline processing system. So we run this tool Legion Prof. It is now written in Rust. I think that was there actually in the last retreat. So that part's not necessarily new. Except that this is now, we have designated it as the one and only way to do this. So Python is now gone. We do all of this in Rust. So there's a process that chomps on those logs and then spits out the actual data, right? And there's a couple modes. I basically took sort of the back end or what we call the front end, the right hand side of this process that actually shows you what the profile looks like. That all got ripped out. And so there's a whole new setup here. So there's a new UI. That UI actually runs both in native and on the web now. So we have a WASM blob. So Rust compiles to this thing called WASM, which is sort of your assembly for the web type of deal, as well as a native interface. And then there's this piece that sort of speaks between them called the data source API. which is sort of the abstraction that sits, between those two pieces. So again, the data source API is sort of like our one unified API that talks between, the part of Legion that, or the part of this that processes the profile and the part of it that actually shows the UI. And the reason why we did that is because the Legion prof backend piece contains all of the business logic for Legion, right? It knows what a task is, it knows what it means for a task to block, and block on various kinds of things, block on tasks, block on calls, and all those sorts of things. And so there is just an enormous amount of complexity associated with that. It is sort of by far the most complicated part of the profiler, and we do not want that complexity creeping into the rest of the system. And so this is sort of the hard boundary where, it's 5 function calls. If you can handle those 5 function calls, like, you can generate a profile. But the nice thing about having an API is that this is really sort of a flexible system, so we can do this dynamically. Like, you can load it up in memory and serve this on the fly, generate all the tiles on the fly, or you can do it statically, so we can dump them into, just some offline disk profile, and that works equally well. Like, we don't really care where it comes from. If it satisfies this interface, then you can use it. And there are a whole bunch of adapters. There's a parallel adapter, there's sort of a deferred adapter, there's a network adapter, right? And everything is sort of pluggable. Like, you can plug one thing into another thing, and all of that sort of works. And so that sort of led us to create this new archive format. And so this is sort of, the nice thing about this is it matches one for one with that API. So if you look through all of these calls, aside from the very first one, which is not really sort of real data, but everything, the 4 things down from that correspond literally one for one with what is on disk. So there is an info blob, there's a directory of summary tiles, and because it's static, you have to pick your tiles in advance. So that's sort of the one caveat. And so, I haven't shown like the full contents of a real archive here, but you can imagine there are more tiles sitting in there, right? And it's just literally like we've chosen a representation that happens to work really well with Rust. So there's this thing called CBOR, which is sort of like a binary JSON. So it's a self-describing format, which is really nice for parsing. So, if you can take a blob of the thing, and you don't really need to know what it represents because like all of the things are self-contained. With Z-standard compression, which is just sort of the nice compression algorithm that exists right now. And all of this sort of works really well with Rust. And then I went and I created the UI that sits on top of this. So we use a UI framework called eGUI. So this is really popular in the game space. So this is an immediate mode framework. So if you think about a video game, you're running at 60 FPS. In a game, right? You can switch your camera around, and so you have to redraw every frame every 60 times a second anyway. And so it's sort of like pointless to save your UI, right? So all the normal tricks you do for desktop UIs sort of get thrown out the window, and the whole point is just to draw your UI as fast as possible. So you have your 17 millisecond timeout or whatever that you have to draw your UI in, and the whole point is to draw that as quickly as you can. And from our perspective, it's just sort of nice, like it came with both native and WASM. So like this screenshot is from the native version. That was just like literally running on my Mac. It's GPU accelerated, like it handles, when I started this work, the first thing I did was I did a test with just like split as many rectangles onto the screen as possible. And it is interesting, like the difference between the GPU accelerated versions and the non-GPU accelerated versions is really, really obvious because it is like literally orders of magnitude different. And so, yeah, so all of this, was written sort of very carefully with performance in mind. So everything is asynchronous. If you have a slow data source, nothing blocks, right? Like nothing ever blocks the main thread. You can have a request outstanding as long as you want. It's scalable. Like the very first test I did was sort of running it sort of a simulated 8,000 node workload, right? So sort of the scale of Frontier roughly, and that's just buttery smooth. Like that was kind of insane because we were dying at like 100 nodes on the old UI. So And it is a tiled format so that everything, I mean, it only loads data for what's actually being displayed on the screen. So I think Mike is actually going to go through and demo this afterwards, so I'm not going to actually show this right now, but there's this whole new UI there, which makes things a lot nicer. Some of the other things I'll just briefly cover. There's also this new layer called p-realm. So this is the profiling interface for Realm. So if you have a pure Realm application, right, today, Legion is responsible for generating the Legion prof logs. But it turns out the logs are, maybe not 100%, but 80 to 90%, sort of, equivalent for Realm, right? Like you still have tasks, you still have instances, you still have, copies, and so on and so forth. And so this p-realm layer wraps around Realm. It sort of takes the API wrapper and approach. And so anytime you call into a task, a copy, an instance, what have you, it instruments all of those things. It takes care of dumping the logging format. And from your application's perspective, you don't need to know anything. And so that's sort of a proof of concept that we're able to make this work. And I think that there may be some further integration in the future to just make it a bit more seamless. But I think this already exists today. It's in the Legion repository. Like you can go out and try it if you're a Realm user. OK, so I'm going to switch directions now. So I talked about the profiling stuff, and now I'm going to talk about correctness. And so we've been here many years, and I'll just make the observation that Legion still has bugs. We still have users encountering bugs on a regular basis. And so recently I asked the question, like, what would it take to get to actually 0 bugs? Like, what would it take to get there? And in order to do that, well, like, we'd have to run all possible Legion programs, right? Is that crazy? Maybe a little bit, but maybe this is something we can actually make progress on. So a fuzzer is a tool that sort of runs randomized programs. And the goal of this is to cover a core set of Legion features. Okay, so it is explicitly not a goal to cover every possible Legion feature, but we're talking about the core things like tasks and privileges and fields and regions and partitions, like the basic things. And we want to cover those things exhaustively. So it is randomized, and so it is probabilistic. But the goal is if you run this thing long enough, in principle, it would eventually cover every possible permutation of operations you can run through Legion. And the goal of doing that is to basically stress test the runtime. So anything the runtime could be doing, like any obscure bug that it might have in some really bizarre, weird corner case that no one would actually encounter, like we want to find all those things so that some poor user doesn't encounter this when they happen to fiddle with the sorts of things that they're doing. So in order for this to be useful, it would be really nice if it were deterministic. It turns out Legion actually makes that kind of difficult because it is an asynchronous runtime system. So there are some things that are deterministic. So the set of tasks that we run, the mapping is deterministic-ish. But it's an asynchronous runtime system. So there's always going to be a limit on exactly how deterministic you can get. But we're trying to push that as much as possible. And ideally, it would also be reproducible. So if you have machine A and machine B, you go from machine A to machine B. Like, it shouldn't depend on the machine, right? Ideally, right? You should be able to take it anywhere you want and run the same set of operations, and just sort of make it easier to debug with that. OK, so in terms of the design, the fuzzer thinks about what I call traces. So this isn't quite like, it's sort of similar, but not quite identical to a Legion trace. But a trace is basically just a sequence of operations. So we're not necessarily running it repeatedly, per se, but we're enumerating some set of things to do. An operation could be a task, a copy, whatever, right? And we're going to choose those things in some way. So we're going to, if you think about sort of making this diagram, we're just going down the field. So you pick the privilege, it's going to be rewrite. Pick a partition, right? Just pick one at random, right? Pick the projection ID, right? And you're just going down these things, filling in all the slots that are relevant. And if you sort of enumerate, what are all the possible things you could twiddle in Legion, right? You stick that into the thing, you randomize the choice, and then you've sort of generated a random program. And we, to run it, we initialize a region tree, with some randomized set of partitions, projection functors, and so on, right? And one of the sort of the key design decisions that I made in this process is the trace selection and execution are just totally separate. So you need the random number generator to generate the trace. There's a completely separate thing that executes the trace. And part of the reason why you do that is you can bisect, right? Like suppose you have a trace that has 1,000 operations. Looking at 1,000 operations, like if something crashes, that's not really nice. And so what you want to do is you want to cut it what if we run the first half of it, or the first quarter, or the first, how short can you make it and still reproduce the problem? If you can bring it, we've found in practice that typically you only need about 10 to 20 operations to actually make the runtime crash, but you need to find the right ones. And so if your trace is changing as you're bisecting it, that doesn't actually work, right? So it's very important that that be deterministic. And so there's a very particular methodology used to sort of make sure that we keep things deterministic as we're doing that. But then, the execution piece of that is separate, right? And you can sort of start or stop in the middle of it or whatever you need to do. So, one of the other major goals for this was to also fuzz the mapper. And part of what that does is it just introduces noise, right? So, in the default mapper has certain heuristics. It tends to do things in a certain way, right? It doesn't try to introduce copies more than it absolutely needs to, right? Which is great when you're actually running, but our goal is to sort of mess with things as much as we can. So we're sort of picking instances at random, trying to generate copies or not generate copies in sort of the weirdest possible ways, and just trying to, in general, force Legion to go down different code paths. One of the sort of the notable differences between this and the application stuff is that mapping is actually on non-deterministic hardware, it is impossible to make it fully deterministic because Legion does not promise how many calls it makes into the mapper. I mean, some of those sequences are deterministic enough, but some of the scheduler calls, Legion could call some unknown number of times into the thing with some unknown number of tasks. And so we do the best we can, but it's not necessarily always going to be a fully deterministic thing. So that's sort of the unfortunate reality. We can't get to 100% determinism short of one of these crazy startup things like Antithesis, which if they ever have reasonable pricing, maybe we'll try them out. But anyway, that's sort of the way things are today. So one of the cool things about this is there's actually a really straightforward way to verify it, right? Because we're running a random set of operations, and so you think how could you ever know if we're just twiddling things almost at random? How is there any sensible answer to get at the end at all? Well, there's actually this really cool thing you can do because Legion has sequential semantics. So in order to figure out what the answer is, you run the program twice. You run it in tasks. Legion does all its fancy dependence analysis and stuff. You get an answer out at the end. And then you run a second copy. No tasks, no Legion. It literally just you allocate a piece of memory, you scribble into it. It's totally sequential. It's all running in one thread. There's no concurrency. There's no parallelism. There are no races. There's no communication. There are no copies. It just literally scribbles on the data. You get to the end, and either they match or they don't. And if they match, then you're good. If they don't match, then Legion is clearly wrong because the other thing's sequential, right? The other thing is truly sequential. And so, for sure that that's the right answer. And so that's sort of a cool way to verify it. And also, it comes with a nice side benefit that we verify Legion Spy. So Legion Spy is itself, the verification routine for Legion. But what verifies the verifier, right? So this tool also sort of serves as a side check because we have a ground truth here, whereas when you're running Legion Spy, it does whatever it does, but at the end of the day, what proves that it's correct? We have no formal verification of Legion Spy itself, and so this gives us some nice confirmation that all of that stuff works. So one of the sort of the key pieces to making this actually work in practice is you need a sequence of deterministic random numbers. So you really can't use anything in the system at all. Even though you can seed rand, rand is not a formally specified algorithm. So that's no good. So we need to find a different way to do this. And on top of that, there are some things we need to be able to do this concurrently. We need to do this in parallel. In some cases, we might need to go backwards or forwards in the stream of random numbers, and so that all just gets weird. And so we figured out this system for doing this, which is basically based on hashing. So the idea is you have to pick some sufficiently strong hash function. In this case, I picked SIP-hash because it's sort of based on a real cryptographic hash algorithm. So this is sort of like a watered-down version of SHA-3 that doesn't, it's not fully secure, but it has some nice properties. And then basically you just hash some tuple of things, right? You hash a seed and then some number of things, and it just depends on like how many components. You have some stream number, right? So we have a stream for the mapper, we have a stream for projection functors, we have a stream for the main application, or what have you, and then within those you can have optional channels, and then you just increment some sequence number, right? So you just, request 0, 1, 2, 3, as long as every input to the hash function is unique, and the hash function itself is good enough, you think like, well, this is really low entropy, like if you're into cryptography, like, which is true. But if the hash function is good enough, you get random enough looking bits coming out the other side. And so that's kind of cool because it sort of alleviates a bunch of the engineering concerns, and it gives us sort of random enough numbers to sort of fuzz the system. Okay, so at this point, I think we've actually fully verified all of the major Legion modes. So we do single node and multi-node. In multi-node, we do DCR and the non-DCR. We do debug and release on all of our tests. And so there is, so we've gone through all of these things. We found more than 14 bugs. That's an underestimate because in some of the GitHub issues, like I just kept going back and forth with Mike as I was finding new stuff. So I'd have to go back and actually count to find the real count. But it actually found multiple non-trivial algorithm bugs, including the first actual bug in physical analysis, according to Mike. So that is my, my quote from now on. Like I'm going to take that to all of my talks. And we found another case where the Legion behavior was actually sort of underspecified, and we actually had like a whole series of meetings to figure out like, wait, like what do we even do in this case? So that was good. Like that was showing that we were exploring a different part of the application space versus what had been sort of just organically encountered by users. And of course, a whole slew of races and overzealous assertions and Legion spy verification bugs and all sorts of things. In addition to realm bugs, which, by the way, the Realm team, guys, really get on that because those are all the crashes that remain at this point. So whenever I look at like the output of the fuzzer, I'm staring at Realm crashes. But it's nice because some of these things we've had them in CI for literally years at this point, and now we actually have a way to reproduce it. So that's sort of the really nice thing about this is we can sort of take it anywhere, run it anywhere, and sort of reproduce things that might be very difficult to produce anywhere else. So there is a really nice test harness. It's totally push button. There's literally one script, right? So that line, you do all. You give it the name of your machine and the branch you want to run on, and boom, like it does everything. It does the build. It downloads all the stuff. It knows all the configurations. It sets up all the tests. So this is not actually hooked up into CI. Part of that is just because some of these tests run for quite a long time. So we run somewhere 2 to 4 hours per configuration, and that's taking up a whole node, okay? That's not like 3 cores or whatever the CI uses. That's like taking up a full 20 cores of the node and like really hammering on it, right? Like these tests really overwhelm the machine for that duration. Partly it's for debuggability, so we can reproduce on hardware we have access to. Containers are great for some things, but kind of horrible for other things. And so just like having a known system like that we can produce these issues on is really nice. And also it lets us run some real world configurations. So we're running on the actual InfiniBand network hardware, right? So we're not just doing the fake network stuff that we do in our CI. Like this is actually doing, hammering on the NICs and doing, true multi-node. So there are some, to-dos that we still need to get to. So we currently cover sort of tasks, but there are some other kinds of operations that would be nice to cover. It would be nice to do sort of some more dependent partitioning ops. We only currently do complete partitions, so we have disjoint and aliased, but we don't have incomplete. And so that's sort of a case that's missing. it would be nice to do some deeper region trees, so that's sort of like one of the extensions that it's not totally obvious how to do that. And then a few of these other things, so I won't read the rest of that, but there's more to do, but like we've made a lot of progress. And with that, I'd be happy to take any questions.